here we go. Number 2 is up first. Hello.
Which means I still had to do all the homework last night. Just presumably. What is it?
I always loved as a procrastinator, and hopefully this is not something you have had to learn, but as a procrastinator when I was in high school especially, I'd get to a test day, and the teacher would stand up in front of me and go, and I'd have like a lot of work. Oh gosh, please do this test today. And he'd be like, all right, test is not today. And I'm like, yes! All right, test is not today. And then I would go home and do nothing. Procrastinate that entire night. And so then you're walking in the next day and you're like, I hate past me. Past me makes terrible decisions. All right. It's as I've grown up and got and become more mature, and in certain ways, not all of them. But the amount of times that switched where I go, man, look at you, past me, great job. All right, moving on. All right, so yeah, this guy's a little bit annoying. The major part that is difficult here, I'll be honest with you, is mostly just is 2 things. One, the level of precision required to get it right. So let's walk through one of these right here. And we'll talk about what's going on here, and the easy part and the hard part, and blah, 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 blah. Okay, so number 1. What is Z? Actually, just what does it represent? Atomic number. So in this particular case, that's, of course, just 25. 25. Okay, and what is Z? I know I'm asking the same question. Wait, sorry, not the number. What is Z? Number of protons. Correct. Thank you very much. That's going to become important here in just a second. So, what is A? What's that called? No, that's not the name of it. Where Z is the atomic number, what is A? No, it's not atomic mass. Atomic mass is that one. That's the average one. So you're right there. That's why I'm just trying to make a distinction. That's why I'm trying to talk with the vocabulary so you have the vocabulary. That is known as mass number. Okay, atomic mass is the average. Okay, mass number is, and this is I think the important thing for me when I was going through this, every individual atom has an integer number of stuff in it. There is no fraction. There is no fraction for an individual atom. There is only a fraction when you take all of the averages. So A is the number of things in the nucleus, the nucleons, if you will. So Z is the number of protons. So what does A minus Z represent? Neutrons. And in this case, that'd just be 55 minus 25, so 30.
Do atoms have antiprotons in them?
No, brother, you don't want to talk about that right now. Okay. Now, the second weird thing about this particular setup is most of these numbers, I think, are pretty consistent. Mass of the proton is specifically in the is specifically in the book. I believe this is the number they use. This I can't remember which problem it is. One of the problems like weirdly changes like the number barely and it affects things. But essentially, if I want to know the total amount of mass, I need 1.00. Let's see here, 7276 U times 25. And this will be the mass. I don't know why I put a mu there. That's not a mu. That's supposed to be a U. I'm just used to it. Okay, that would be the mass of the protons. Plus, we have the mass of a neutron is 1.008665 U times, we just said there's 30 of them. Probably pretty basic for you. The first weird thing about this particular problem is that it tells you the mass of the electron. The fact that it tells you the mass of the electron probably means it's going to be involved. Now, why do we usually ignore the mass of the electron? No, that's not why. Not already.
The book said it was sometimes.
That's what we're addressing right now. So when is that sometimes statistically and why that is? The answer is, the reason why we normally ignore the mass of the proton is, look how freaking big it is relative to the mass of the proton over there for the most part. So, go ahead.
The differences between the masses are so small, you think the mass of the proton would be significant.
Do what?
Since like when you are doing any of the things, the difference between the masses is so small, you think the mass of the electron would be significant.
Right. That's what I'm saying. You would think that usually it is, and in this particular case, it only isn't because I mean you can calculate it right now, and you're welcome to. Okay, if you calculate this out right now, and then you calculate the addition of the electron, which you do have to do. So let's go ahead and do that real quick. Let's go plus 5.486 times 10 to the negative fourth u times how many electrons are there going to be? 25. Where do we get 25 from? Equal number of protons and electrons, even 3. Okay. If you compare it before to after, what you will just simply notice is that it does affect it at the fourth significant figure. Because it specifically addresses the fact that it is 4 significant figures, that's about how far over you gotta go to hit where the electron is actually gonna make a difference. Now, do we usually worry about the fourth significant figure? No. Why does the fourth significant figure matter in this particular case? Because of the amount of energy that even that decimal place can have in this particular case. Next, it tells you what the mass is of the collective atom by itself. So what is this that I'm calculating here? What is this that I have calculated there?
The mass of all this stuff that makes it up, mass initial.
Right, the mass of all the individual pieces. So putting this all together here real quick, 7276 times 25 plus 1.008665 times 30 plus 5.486 e to the negative fourth times 25 again. And I get 55 point, I'm just going to write more decimals than I need to here because it wants 4 significant figures, but it's 4 significant figures on the decimal, not this guy. So let's just go 63, I'm going to write everything. Minus what was given to you here, which was 54.938048. So I'm going to subtract 54.938048. So where I go into this giant thing throughout all of physics and regularly talk to you guys about just drop decimals. Why are you doing this? This is the time where I am going to be pretty hardcore and say, yeah, you're probably writing everything on that calculator and writing it down on work. So I have a difference of 0.5183. Let's check. You do it. Let's see here. Oh, I got it wrong. Okay, where did I get it wrong? Let's check again just to make sure. .077276 is 25 plus 1.008665 times 30. Man, this is annoying. Putting in just a single number wrong. I put in 5.786 as opposed to 5.4. Listen, we have discussed this previously. But I'm happy to discuss it really again. There is what Spainhour does to you and what physics freaking actually is. Now, I am happy to take a certain amount of ire throughout the years from AP physics students who are struggling to come to terms with the difficulty of physics versus Spainhour being an ass. Okay? I'm happy to take that and just say, yep, I'm the villain. Okay, just do your work and become a better person. And even if you think I'm a villain, if this makes you a better person, I'll suck it up. But you, who are in the latter part of the physics too, and have seen me, hopefully you believe this, and if not, it's totally your prerogative. You don't have to. Work my ass off to try to help you guys become better people.
My ire was directed at physics instead of you.
Okay.
You should probably just like be
Fair enough. I believe I can usually hear it in the tone. But all right, you do you.
You don't know who the ire
I don't. I 100% guess. All right, here is the annoying thing as well about this problem. Okay, number one, they don't tell you this. They should, and we don't usually use sig figs, so you don't know this. This 4.0 with the little line is not saying it's 4 significant figs. It is, but it's saying what that is the symbol used throughout all of this program to tell you that significant figures matter. Okay, now if you had done significant figures throughout all of physics, you would just be used to this symbol, and this symbol would say, hey, pay attention to sig figs. That's all it's meant to do. It's annoying because this is the first time you get to it, and it makes you believe that both of these are supposed to be 4 significant figures, and you go back and read the instructions here, and this one's supposed to be 4, and this one's supposed to be 3. Again, I apologize. That is a matter of, if you want me to hurt future physics 2 students, I'll just make every problem in all of your homework across the board require significant figures, and then they would get used to this symbol, and they would know that's not an issue. But moving on. So all you're going to do here, of course, is take that number, multiply by 3e to the 8 squared, to take that amount of mass in you. Oh, no, I'm wrong, because that's not in kilograms. I'm wrong. So taking that number again, hold on. 0.517517 multiply by 938. 931. 931.5.
Yes.
Okay, 931.5 to get me how much this is in mega eV. That is EB. EB is the binding energy by just taking this number multiplying by the 931.5 to get you, but that's not what it says. Binding energy is looking at the amount of energy per nucleon. So all you do is you take that total number and divide by the nucleons, which is 55. And I have 8.76 because it just wants 3 significant figures. Let's check to make sure I have a green arrow, and then we'll move on. All right, I'm not going to do the other 2, but are there any particular ones that are sticking points for you that you are? This happens from time to time. I seem to be getting 1 and 2, but 3 is being annoying. You guys are good? Questions on how to do this?
Did you just divide the last one by the number of nucleons?
Yeah, that's what it says. It literally says that's the ratio right there. EB is the binding energy, which was taking this and converting it to the energy by multiplying by 831. That's not what this says. This is not asking for binding energy. It says binding energy over, this is why I was highlighting A earlier. A is the number of nucleons. So I just divided that answer by 55, and that's where I get this number. And the reason why they're specifically focusing on that number is, if you look at this chart right here, that is 100% what is over here on this axis. So Mn that they just did is somewhere right in here. 8 point, what did we just get? 8.76. I think we're kind of sitting right in the heart of actually this guy right over here. So if you look at Mn, Fe, and Co, the 3 that they're doing right there, they're right there. And they're looking at what you should end up seeing, I believe, is that iron is the tippy top of binding energy. It's going to be small, big, small again afterwards. Questions, concerns about that? Moving on. Number 3. Okay. So Fe, we're asking for this one? Yes? Who's asking for number 3? Okay, cool beats. Okay. The fact that it says 56 and 56 means that this is beta, right? Okay, now what you want to look at is natural beta decay. Well, it's not natural, I should say that. Normal beta decay is a electron comes out, and what else? Neutrino. Thank you very much. Okay, and because the electron comes out, a neutron is converted to a a neutron is converted to a proton, so actually the element goes up. So in this case, I look at iron and cobalt, and yep, it is in fact going up. So it should be, I'm sorry, which order is it? Okay, so this is actually looking at which one of these is probably more likely, okay? And the answer, so what do I look at specifically very quickly in this particular situation to figure out which one is the more natural way to go? which one has more mass, should be the initial one, right? If you can go the other way, you just need to input mass in order to do it. It's kind of like looking at if this is mass is serving as like you look at a ball on a hill. Can you put the ball up the hill? Sure, you got to put input energy. Which way is the ball naturally going to go? Down the hill. So in this particular case, it's going to go from the higher mass to the lower mass. So it should go from cobalt to Fe. Okay, going that should lower that particular process since the atomic number is staying the same. I know it is either beta decay or, well, it's beta decay either way, whether it's the positron coming out or the electron coming out. So this would be the electron coming out in this particular, sorry, the positron rather coming out in this particular spot, because if the electron comes out, you get a proton, it goes up, right? The positron comes out, you get an antiproton, so it goes down in that particular case. Okay, number 4. A beam of 7.73 mega eV protons is incident anytime it says like that. That is a simple way of saying that, hey, the protons in here each have a kinetic energy. That is specifically kinetic energy that is incident on the target of 2713. These protons collide and produce the reaction shown below. It tells you what the mass of the SI is, neglecting any recoil of the product nucleus. Determine the kinetic energy of the emerging neutrons. And by the way, if you look at the math, it does kind of work out where, yes, should the daughter nucleus have some kinetic energy? Yes. But as we see with kinetic energy, the relative amount of mass, since the neutron is so much less mass, it should carry away a vast majority of the kinetic energy in this particular process. So, strange that it tells you SI mass, but it doesn't tell you the mass of aluminum in this particular case. But
SI was on the table.
yeah, and that's why I think it's strange. It should be. You guys have messed around with the table, yes? Yeah. Okay. So where I shouldn't be asking you this. I apologize, but where do I have the table? Is it on? Obviously, I know it's on Google. Well, it's on the notes as well. Yeah. But I thought I put it.
Like
Yeah.
in classwork, if you go to the notes, it's the other option, like the right.
There it is. Chapter 29, the abbreviated table right there. So there you go. So we need aluminum 27. I said that right, didn't I? Oh, I'm going wrong. Aluminum 27. It's actually the only one on here. So I'm going to take the mass of the proton, I think is we're starting off with here. So let's go mass of the proton. Proton should be right up here. Ooh, does anybody see proton's not directly up here? But yes, it is. Yep, hydrogen right there. 1.07. Hmm.
Because I know this. It said in the book the table had the mass of electrons and nucleus N.
Mm-hmm.
So does that one have that?
The electron would be 5 times 10 to the what? Negative fourth. So I believe that would be, let's go, 1, 2, 3. Yeah, it should technically be right here. Okay, so you'll notice, boom, atomic mass, chemicals. So yeah, you want this guy right over here. I don't think so. No, what is? I don't believe it is. I think that number ends up being correct. 1.7825. I'll check it just a second.
So is chemical with electrons and atomic mass is no electrons?
Chemical is the average. Chemical is what you're looking at right up there.
Oh, okay.
Chemical is the average of all the isotopes. Yep.
It's
What?
slightly bigger than the mass of proton given by the thing. Or no, I was looking at the chemical one.
But
Actually,
mass
so.
does.
Well, then they just had it right up here, so we can use this one too. 1.7276. All right, I'll use that one. There you go. So plus 27 aluminum. 27 aluminum just was right here, so that should be plus. And I'm using these over here. Okay. Of course, you can tell you have to use these right over here because carbon only has one number. Why does it only have one number? Well, because it's the average of all of the things. As a matter of fact, it's a combination of these three things with these. This is the percent abundance of these particular amounts in that particular guy. But here we go. So we have aluminum should be this 26.981539. 26 point, what did I just say? 981,539. U. So this will be the total mass initial. You can do this however you want. I usually just do that. Move it over here, and now we need, oh, this one's told to us. Okay, the mass of SI is, well, yeah, we'll just do it across the board in order. 26.98671 U. I'm subtracting the entire quantity plus the neutron, and the neutron, I believe, is on this list at 1.008665. 1.008665 U. So we have the initial 1.007276 plus 26.981539 whole thing minus 26.986721 plus the 1.008665. Hold on, I have to speed that up. 0.8665. Making sure that that's right. And you get a negative number. What does that mean? Energy has to be added, correct? It also means, if it helps a little bit later on, that this is not a quote-unquote natural process, that it would be endothermic. It requires energy to kickstart and get going. So we need to figure out what this is in mega EV. So this conversion from U to mega EV is why it was important early on. It's multiplied by 931.5. Oops, that's dumb. Okay, times 931.5, and you get negative 6.12 mega EV. We started with 7.73 mega EV of kinetic energy. So basically it's this. It's your kinetic energy initial plus the Q value. So plus the negative 6.2 mega EV is equal to your kinetic energy final. So I have 1.61 mega EV. What's up?
You'll see.
You said that there's a good chance it's not right?
Yes.
Yeah, I think I did it.
And I have a theory as to why.
Okay.
Even though it gives you the isotope, there's technically one less electron than that isotope is counting for, is what I ended up looking and seeing as giving me a right answer.
Well, let's do this first. Let's check the table first. There is, so aluminum's right here. Oh, this is why they told you silicones. They told you silicones because it's not on the list. That's why.
When I read the book and it said that electrons are included, I thought that might be what they're doing to us, and that is, it gave me a check mark, and I did do that. So I don't know.
Yeah, so whenever we find Q, we're supposed to do electrons, like like electrons to be 100% accurate?
In beta decay, you shouldn't.
All right,
like,
what? Here it is.
the isotope.
Here it is, and this is annoying, but I'm not honestly sure why they do. This is literally what I was talking about earlier. It has the work here exactly what I just did. The only thing that is different is mass of proton, and the mass of proton is the one that I did earlier. It's the 1.007825. Now, good news, bad news here. The bad news is that's annoying if that's the only thing that you messed up.
That is adding the electron though. That's what that does. Like that's just why I like.
I'm with you. I'm with you. Okay. I agree 110%. Okay. So yeah, it's annoying that is ultimately what the issue is. The good news is if this were to happen to you on the test, I will not let you miss points for that particular type of situation difference. Yeah.
So if in my work, I use the massive proton that they give in the original thing, and then I add the massive electron to the subtractive.
I would suggest usually using the proton's mass that's on here, which is the hydrogen. I would suggest using that guy right there most often. I believe if you use that guy most often, not the individual proton, but the total. Well, here's the thing. So, yeah, it's.
So if my work does right now, my work
It's
is
debatable.
proton,
It's debatable
yeah.
because they're saying proton, right? How do protons usually come? Protons usually come as hydrogen. That's where the most predominant element throughout all of the universe is hydrogen. Are they usually going to have an electron on them, or is the electron usually going to be shed? Usually they're going to have the electron on them. So it is confusing and anti-intuitive because it says proton, but on top of that, I will also add this. Where's it at? Which one did we just use? Did we use this one?
This is the one.
No, this is the one I just used. Yeah.
Yes. Because it has.
Yeah, I'm with you. I get. I believe. So let me just check to make sure that is all that would change my work right here.
When the gamma decays into protons, they don't have electrons, right? Like when it decays into a proton and antiproton, they're just free floating.
They should not. No, they should not have one. Here. So this should have been instead of 1.007276, it's 1.007825. Okay. Now we subtract 26.986721 plus the mass of the neutron, which should not be different, 1.008665. Okay, slightly different, 931.5. And then 7.73 minus that amount of answer. Oh, nope. So now I have 2.12. I don't know if this helps or hurts. I disagree with their use of that mass. I don't think it is correct.
But what I was.
I think you were trying to think very deeply about something that the people that made this problem did not think deeply enough. And I'm fine with that. I'm fine with that reasoning. But you're putting a line of logic into, well, they thought this, and this. And I don't think that they did. I think that the person that made this answer key was probably a grad assistant to the person doing it and did not put the level of thought into it that you're putting into.
When I read the book, it did say the isotope masses include the electrons in their mass. That's why number 2, we have to count the electrons. And then this one is an isotope mass, but technically that isotope didn't get an electron from anywhere. Like didn't get an extra electron from anywhere. The aluminum, like it didn't gain it, so it's not over there. Is what I did.
You're fine. Again, I like this conversation, and I could dive deep into this conversation, but it's kind of pointless if the person that made this did not have that similar level of conversation. It's the whole, the infinite number of monkeys could type Shakespeare, and us doing a deep doctoral thesis on why they decided to type Shakespeare. It was flipping random. It happened to work out where it was an intelligent thing. They didn't know what they were doing. Yeah, what's up?
Like throughout the homework, I've had a lot of problems with trying to decide which masses to use on which side of like the reactions.
Okay, can you be specific to?
Or finding cues. So like, what is like the most accurate way? Like, should you only?
So go to this chart. Go to this chart and specifically look up the isotope in question. This is what they are using through and through all the way. Okay, now the conversation that Trenton is having, that I tried to put a little bit of a kibosh on for the sake of efficiency and because I think he's putting more effort in than the people who wrote it, is a very decent one and a conversation to be had at a high level. I just don't think it's one that you guys need to focus on primarily right now. So I'm happy to go through the problems that you're struggling with and look through, but if that is what it is, I don't want to spend a ton of time on it because it's a matter of you have the concepts right. You're not using the right fifth decimal. It's annoying when this is why I ignore sig figs throughout pretty much the rest of physics on why you can use them, when you can use them, is a little bit more of an art form necessarily than always a direct science, which is why it gets annoying.
I just wanted to see your answer again for the amount of EVs because I have a different amount of like starting EVs and I keep getting mine wrong for some reason, so I want to make sure.
Well, we should have the same Q, right?
Yeah, that's what I'm saying.
So what's your MEV to start off with?
6.93.
6.93.
Yeah.
The main thing I'll say, so I have 2.32 for you. I'm sorry, 1.32.
Okay.
Is that what you were getting?
I was getting like 1.2 something.
So write in 1.32, see what you got. Yeah. That's the other thing here is it's the cut and dry of 10%. 10% can mean like you're still getting it wrong, but it's within 10%, or in this case, 10% means you're barely getting it wrong whatsoever. Main thing I will say regularly in this is just make sure you're not rounding early. Use all the numbers.
Made you get more precise than 10%. It said you're
Correct.
within 10%,
Right.
but that's not good enough for us.
Yes.
So when you're finding Q, it's just nucleons, right? That you're worried about? Or
No.
no?
No.
Like,
But that's why I suggested the chart, because this has everything in it. Okay. All right, back to our regular scheduled programming. We're on number 10. What's that now? Oh, okay, sorry. Do you guys know the shorthand for writing these, by the way? Do you know like the shorthand for like upper sort, like you know that you can use the underscore and the caret to write these way faster? Do you know what I'm talking about?
What's in the caret?
No, I'll show you what I mean real quick.
You mean like the underscore and the caret?
Yeah. Okay, so write the complete decay formula for this right here. So here I go. It has so this undergoes beta decay to get to calcium. Just checking to make sure. Yeah, that's K going to Cl. So and it says write the antineutrino as V. So this should be K underscore 19 caret 40.
Does it work if it's not sound? I never tried.
There you go, and you see it right over here. Okay, writing the arrow, and now we have. Oh yeah, you should be able to write the. Isn't it just? So let's make sure it's right. Plus, this should be CA underscore 20 caret 40 plus. This is
I think you have to put it before.
Yeah, I think you do that. We might have to.
do what?
Put the letter after the numbers.
No, I don't think that's true.
I did every
At least not in my experience, but it might be I need to put a space here. So let's see. Potassium underscore 19 caret 40 space. Or maybe there is no space. Arrow. I've done this a bunch of times before. No ways. Okay, so plus again CA underscore 20 40 40 plus that might be spaces here. Yeah. Spaces. plus that should be, and maybe you're right. Let's try it the other way. Yeah, I think that's true. E underscore -1. Sorry, E -1. Okay, 0. Oh, we're doing it wrong. Ambiguous or incomplete reactions. I think it's. Oh, I didn't put neutrinos in there.
You entered never too much for useful feedback.
Oh yeah, you could write new too.
We can't provide useful feedback.
I do want to use it. So this should be what, 234. So maybe you're right. Maybe it's and maybe I'm doing it in the wrong order too. Underscore
I don't think that worked.
2. So that's right. So let's try this again. So you might be. Let's try this again. Underscore 19 caret 40 K yields underscore K caret 40 CA plus underscore -1 caret 0 E plus new. Just a heads up about tomorrow's test. There you go. Yeah, so this is right. So you were right. I have to put the letter last. Okay. Yeah. Beyond that, I don't think I'm going to do this in this bottom part unless you're really struggling with that part. Things I'll highlight on it is number 1. It's literally what we just did a second ago. It's find the energy of this. Here's the energy of that. You do have to deal with the mass of the electron in that particular case. Nu, if you remember, why don't you have to worry about the energy of nu?
It only maybe has mass. That's what the book says so many times.
Yeah, basically it's for our purposes in here, it's 0.
I don't think you need to count that mass of electron though, because it's in calcium's mass, like in the isotope calcium mass.
You know, so the difference between those two should be it, and then also do notice that this is kilo EV, not mega EV.
You don't have to account for the initial energy.
That's what I was trying to say earlier when I.
Why don't you have to account for the initial energy? Nope, it's not working. This mass is bigger than that mass, right?
Yeah.
So it could start entirely from scratch on its own.
This hurts.
Yeah.
Why?
And it's the maximum energy of emerging electrons, and so yep, it would just be the difference between those two right there. Oh, that is the other reason. Yeah.
Crashing frequency, they call it lambda.
What is the unit for lambda?
Hurts.
And
Well, technically, okay, I wouldn't say hertz because it's technically not a frequency. You can think of it as a frequency, it's not. So but it's similar. It's s to the negative first. It's one of the rest.
You said S?
S to the negative first.
Seconds. Seconds to the negative first, or one of the rest. Okay, we just did 10. I don't want to go past this if anybody is struggling with that last part. Is anybody really needs me to go over the 10 part? I think literally all it's going to be that I looked this up though is going to be the mass of calcium 40 minus the mass. Sorry, backwards of that mass. Which actually no, I think it's right here, isn't it? It's like you don't even need to look it up.
So you don't have to account for the electron?
No, he's right. He's right. The electron that is in there, if you remember beta decay, the electron comes out of the nucleus, right? So that would already be considered part of this particular nucleus right here. So 39.96399, okay, minus that number, 39.962591, is 0.001399 times 931.5. I have an answer of 1.30. I have done it correctly. I'm sorry. No, that would not be right. Yeah, because I made it mega electrons, so it would be. Oh, no. It would be bigger than that. There you go. Yeah, all I did is find the difference between those two. Convert to mega EV and then convert mega EV to kilo EV. All right, next. Suppose any is struck by an alpha particle, releases a proton and a product. What is the product nucleus? Well, okay, so alpha particle means this would go up to 24 and this would go up to 12, but it released a proton, which is a 1,1. So that means this should be _9 caret 23. And what's that? On the bottom?
It goes up to 12. And
Goes up by 2, but it lost a proton.
Wouldn't that go down to 11?
Yes. Just doing my math down. 23, and what's 11 up there? An 8. Ta-da. Alpha particle and product nucleus are produced when sodium is produced by a proton. So what is the nucleus? Once again, go up by 4, down by 1, go up by 2, down by 1. So this should be _12 caret 26. And that's carbon, right? No, what am I doing? That's not carbon. Carbon's 12 is mass.
Yeah, carbon is 12 mass.
Yeah, that's what I was doing. I get out of practice. What I do? Oh, that's why. Alpha particle. Okay, these are produced. I see what happened. I did the opposite. I did an alpha particle hits and gets a proton. This is shouldn't it be the exact opposite? It shouldn't it just be what you started with? Yeah. Because you should go. This should go up by 1 and 1, and then you should lose 4 and 2. So yeah, this would just be that right there. I just did the same thing, but I can't. So it should be 10 caret 20. Okay, next. 20. A head-on collision between two protons with velocities near the speed of light at a large hadron provider in CERN media has shown dozens of new particles produced after collisions that are not fragments, but new particles created after the collision. The only way this can occur is if there's an equivalence between mass and energy where some of the kinetic energy of colliding particles are to the rest of the new particles, is what I would say. Certainly be wrong. Huzzah. Questions on why I chose what I chose? Or why I didn't choose other ones?
Isn't because of rest energy particles?
It's equals mc squared. If you remember, mc squared is rest energy. Okay? The actual kinetic energy in relativity gets super weird and super wonky, but it's this. It's kinetic energy. Kinetic energy is actually equal to total energy minus rest, where total energy is gamma mc squared, minus mc squared. Now, the confusing thing for most students walking into this definition of kinetic energy is they go, where is velocity? I am used to the 1/2 mv squared that's up there. Why is 1/2 mv squared not here? And the where's velocity is right inside that guy right there. Which means that when an object has no velocity, then this essentially goes to 1, right? And should have no kinetic energy. Okay, well, this also says that this would be the energy it does have. The total energy that it has when at rest is in fact then mc squared. Or another way to say this is that, okay, so this says kinetic energy is total minus rest. If I rearrange this, then total energy would equal kinetic energy plus mc squared. So if it's not moving, should it have kinetic energy? No. But that would mean it still does have energy in the form of mc squared. So E equals mc squared is not a complete equation. What it is part of this particular equation right here that is used when you are looking for the energy of the total kinetic energy, but its indication is that objects are not moving do instead have energy, and that essentially the energy is just a conversion between mass and itself. Okay, next number. 26. An alpha particle collides with a hydrogen nucleus. Protons are released along with what other nucleotide? When alpha particles, well, okay, so 28, alpha's 4,2, so that's going to be 18/9. 18/9. The only other one possible would be this one here. Now, it's confusing because it says protons and you don't know how many protons. But what you know is that a proton, chemical definition, is 1/1, right? So if a single proton is released in this particular example, we would go from 18/9 down to 17/8. This one right here. If another proton was released, the next possible option would be 16/7, which is not up here, right? The next possible option would be 15/6, also not up here in any particular way. So there are other options other than this one here, but this is the only viable option of those 4. Does that make sense? Cool beans. I think we're on to chapter 30, if I'm not mistaken. Yep, chapter 30, number 5. Out of curiosity, pure curiosity, fist of 5 this chapter, how we do. It's not too bad mathematically. I think where students usually struggle, and I try to do a good job of this, is holy crap, how big is this topic? What do I have to know? Okay, and I think that hopefully the homework as well as the conversation at the end did a decent job of kind of directing you towards, okay, as messy as this gets, let's focus on what's going on in this particular section. Find the energy at MEV in the fission relationship below. I'm happy to do this, but this is simply going to be add up all the masses over here, add up the masses over there, take the difference and multiply by 231.5. It has not changed that much at all. Yo, what'd it do?
Okay, wait, no, never mind. You answered that question earlier.
What's that?
They give you the stuff for the ones that aren't on
Yeah.
the table.
That's when you're usually going to see. There are ones where they give you everything, but usually the ones they're giving you are not usually on the table. By the way, if you do notice that technically one neutron will cancel with one neutron over here in terms of energy, which you might go, wait, why did they put it up there at all? And of course the answer is that, as if you remember with the whole conversation with uranium, you do have to have a neutron going into the nucleus just to bombard that process. And usually, if you'll remember, what is the average number of neutrons that come out? 2.5, yeah. mass. I said 3 originally, but when I adjusted it later, yeah, it's technically 2.5 with all the things that can potentially come up. Obviously, this one would be 2 coming out in this particular case. Yes. Yes.
Like twice, and it was like,
Yeah, it's annoying a little bit that you would think in a subject that is so ridiculously complicated, they would nail home, like, let's hit all the details. But I'll tell you the truth on textbook production and what I would hypothesize happened. I said earlier, I said that I'm pretty sure that it was a college grad who wrote the answer key, which I think, based on a lot of the problems I've seen on this, is 100% true. Here's the other one. They got to the end of the book, okay? They go, we know our publisher requires this to be in here. But what percentage of high school physics classes ever get to the actual end of the book? Very, very low percentage, and so they probably did not do as much time proofreading that as they did torque and forces and kinematics and all that other fun stuff. Okay, number 10. Again, I'm happy to do these if we have some extra time here. I just want, okay, which of the following comparisons between fission and fusion is true? Fusion produces more energy per unit mass than fission. Fission reactors are easier to build. Not true. Fusion is the process. Sorry, that is correct. I'm sorry. Number 2 is correct. I have that backwards in my head. I always get fission and fusion. Why did they make those words so similar?
Fusion's like fusion.
I understand what it is. As someone who teaches it, I mean, listen, I know that one of my children's name is Jack. I know the other one is Luke. You want to know the percentage of the time I screw that up? It's a lot when you're trying to talk quick and talk through big concepts and everything. It's kind of hard to make that definitive decision when... Anyway, my apologies. Yes, fission reactors are definitely easier to build, so 2 is definitely in there. Fusion is the process by which stars produce energy. It should definitely be 3. I believe number 1 is also correct. I think it's all 4.
And in what way?
That was my curiosity.
What does it mean specifically per unit mass?
What do you mean?
Does it mean like in each reaction, how much mass is in each reaction, or how much massive fuel we have to put in total? Or
I would guess it's the amount of mass that you put in total. That if you look at, obviously it's easy when the mass of hydrogen is basically 1, right? Hydrogen into helium, you're talking about 1, and if you get a decent amount of MEVs out, that now you go to uranium, 235. So
even though
obviously vastly more. So even if you get more interaction, you get more energy out in a fission reaction, a singular fission reaction. That's why they're locating it on terms of energy per unit mass. Yeah. Yes.
Can you go back up to the question in chapter 30 that's about like the momentum and kinetic energy? That one.
Oh, sure. Okay. Is it this one?
Yeah.
So here's the main momentum conversation that's regularly had. I don't know what's here, but I think it will apply, and I want to keep it as simple as possible. Okay, so the main one when it comes to alpha radiation is this. Okay, first thing, you have to have conservation of momentum, conservation of energy. Okay, even though weirdly now mass and energy can go back and forth, so it's not exactly conservation of mass and energy, but since they're the same thing, they're just one big rule now. Like at the highest level, there is no conservation of energy and conservation of mass. There's conservation of energy and mass, collectively, which is kind of what we're dealing with here. So here it is in a nutshell. If I begin with the nucleus, okay, this is going back to momentum. This is Spainhour getting out of a super heavy boat. Okay, this is Spainhour on the skateboard, almost killing himself and putting a skateboard in the wall yesterday. Okay, it's all the momentum to begin with. The thing is just sitting there, has to be 0. So boom, the bigger thing going that way, the tiny thing should go fly that way. Conservation of momentum. Conservation of energy, it's weird to see until you think about it in terms of mass, because you can't go from something just sitting there to taking off with kinetic energy if it did not gain that kinetic energy from somewhere, and it does gain that kinetic energy specifically from losing its particular mass. Now that is alpha radiation. Beta, the reason why beta has this whole new force that messes up the standard model and kind of does all this thing is because the electron does not shoot off with all, I mean actually a very small fraction of them do, but ridiculously small fraction, with all the kinetic energy that it's supposed to have, starting off in the difference between those masses. So that's thus the neutrino was particularly introduced to conserve momentum and kinetic energy in that case. So Compare the final values of momentum and kinetic energy in all this case. Let's see, the initial momentum associated with N1 is equal to that, plus the gamma ray. So the initial momentum is equal to that. Kinetic energy of N1 should be equal to the kinetic energy of the uranium and the gamma ray. Kinetic energy does not have to be the same. Kinetic energy doesn't have to be the same because they are changing amounts of mass. Like 239 uranium and 238 uranium are not inherently the exact same amount of mass. What's up?
I get that the momentum from the neutron has to equal
I got this one right here.
that's what's right. But how do you know that the kinetics greater? Because it doesn't tell you how the potential is, or how
If you don't know, let's go
distributed.
238 and 239, right?
I don't know if they were both. I remember trying to do it, and I don't remember why I couldn't.
Because I know the momentum is definitively greater, but I don't understand how you know 100% the kinetic energy is greater because you don't know how the energy's distributed.
Sure.
Weren't the other ones all impossible though?
I think that's really what it comes down to is test taking strategy of the others. So here it is in a nutshell. Okay, here it is in a nutshell. Here's me test taking strategy real quick. Number one, the momentums have to be equal. So I knocked out C and D. Okay? C and D both say the initial momentum is greater, the initial momentum is greater.
Well, for C, it just says then uranium. So you don't really.
Sure, that is true. I think that essentially, you're right. It does not say plus. Oh, that being said, well, okay, I was going to say the gamma doesn't have momentum, but essentially, I think what this boils down to is that they should have added the alpha in there as well. But A is definitely okay. So if I use that, and I'll come back and address that potentially in just a second. I don't like the fact that it says that it doesn't make them consistent, but yeah, it should say the gamma as well. But coming down to these two, the separation is what you heard me say just a second ago when I saw it say that the kinetic energy of this guy has to equal the kinetic energy is equal to the kinetic energy of this guy and that guy right there. That is essentially what it's saying because it is. You'll notice here it says the original uranium is at rest. Okay, so the original uranium is at rest. So the kinetic energy coming into this has to equal those two. The only way that's true is if these two masses are this mass is identical to the combination of this mass, which is not the case. It's just not going to be the case. They are never equal to each other due to binding energy and that particular stuff. So
does the greater number always have more? When you have more neutrons, do you have to have more binding energy, or does it depend?
it depends on the reaction. A lot of stuff's going. Essentially, what you're asking there is Q always have to be negative, or does Q always have to be positive? And the answer is no. No, it does not. You can end up with more mass or less mass. Yeah. Sure. Yes.
Can you rank the radiation damage? Because I know
Do what now?
the radiation damage between gamma, alpha, and beta. Because I know which ones are more penetrating, but in a different energy sense.
Sure. Gamma's most damaging, followed by gamma has the most kinetic. Okay, here's the difficult thing here. Here's the difficult thing on how they rate it, and I believe they're going experimentally. I do believe I have that backwards, and I'll explain why. Okay, if it makes contact, gamma would be the most damaging due to the fact that it has the most energy, simply put. But the conversation that we also had is the relative size of the atom. Gamma rarely makes contact due to its relative size relative to the size of the atom. It's very small, and so, like we talked about, when you get down to that level, you are mostly empty space. Most gamma radiation slides through unaffected. So there's kind of a balancing here of it would do more damage if all of them hit. Not all of them are going to hit. And I think so. So yeah, penetrating is the easy one. Gamma penetrates the most, followed by beta, followed by alpha. And I think it is in fact the reverse of that for damage, even though alpha doesn't do as much damage individually. Pretty much every single alpha thing that heads towards a person is going to hit because it's the relative size. It's essentially the difference of if I launch, if you guys make a line, okay? If you guys make a line and I just kind of standing next to each other, okay, kind of like maybe this far apart, like normal distance apart, okay, and I threw 30 tennis balls at you. Tennis balls will do more damage, but if you want to talk about total damage, most of them are going to miss, right? Whereas if I send 30 kindergartners and say they have candy over there, okay, pretty much all 30 are going to hit and do some type of damage and therefore add. So that's why it's weird to talk about total damage, and quite frankly, it'll come down to experimental in that case. I don't think there's I would guess that's what the book talks about too. Would have to talk about it. And I don't think that there's damage on the test. Real quick, heads up, the test tomorrow is the first one and only one that is entirely different. I do not like the questions that I had out of your textbook as options. Also, I do not like that your textbook is so particularly specific here. So this is going to be the one time where like the test is going to look probably similar to last year, in which you're just going to get a piece of paper that has a multiple choice followed by the problems. Just like you did last year, and you'll do all of them. Actually, it'll probably be two separate, but it's the same type thing. It won't be online like it has been. So that is meant to give me more options on like how I present this stuff, as well as I don't have to be as finicky with being, you guys don't have to be like annoyed and essentially you don't see the right answers. But most people do really well on this test. This is not meant to blow you out of the water. I'm not trying to like get to the fine points of this. It is hitting big topics and subjects that you saw the AP questions that I kind of went over the other day. They're really not that hard on this subject. If you know anything at all, you'll probably ace them. Yeah.
I need to know 30.9, which is electro theory.
No.
It says it on the topic list.
Yes.
Yes. It says it on the topic list.
Only reason it's excellent point.
Huh?
Did you read it?
I read like half of it.
What happened?
And then there's like, because I read through 3, and then I skipped to 6, and then
Yeah, so the hard thing about reading chapter 30 that way, the moment you skip ahead, you go, so when did they switch to science fiction? I don't know where in the last 3 sections they did that.
And I was like,
But they're
I'm
like,
looking at the
my big
sections,
thing
and
was,
they're not that large.
I
was like,
hated-
What did they do?
there is an acronym that is discussed in the color theory. I think it's QCB. And I'm like,
Oh yeah.
how common is quantum discussion that you feel like through the entire script you say it once, and then we're all like, oh yeah, QCB. Yeah, quantum chromic.
It was like
Quantum chromo.
QPC or something. I was like,
That was annoying.
What was that? I did read that, by the way. It was a lot of stuff.
I reiterate what I said earlier, that I think we are getting into the finer points that they did not themselves. You know what I think they did, in all honesty? I would guess that the publisher of this just flipped like this. They did not care what the words were. They just they flip through, and they go, this looks sciencey. Do I think a bunch of high schoolers are going to buy this textbook? Yes. Yes, I do.
Where's the
Good
8th
enough.
What's the 8th one? I don't remember what it was, but it sounded goofy to me.
The 8th one?
You'll see it.
Oh, the eightfold way.
The Eightfold Way. That's a goofy name.
Yeah.
It sounds like a fictional martial art.
Oh, you want to get worse? So did we
Strangers
end
is
up?
goofy too.
I might have talked about a couple of other guys last year. Did we talk about the 10th dimension?
No. Wait a minute, hold on.
It's a theory. It's a theory. It's a theory.
What happened?
so we need to know at a point 9 tomorrow. Because I need to know if I need to like try to sit here and just memorize
Do
it.
not.
Because
Again,
not
I don't
like
want.
that.
I want you to know the basic concepts, all of which I have discussed up here. I do not want you to freak out at all on chapter 30 and get into the weeds of chapter 30 in a nutshell. Okay? What do I want you to have out of chapter 30? A basic tenet understanding of essentially the 4 fundamental forces, which you already have. A connection to a little bit of the understanding that there is a particle medium between the two. You don't necessarily need to know which one, but photons protons is electromagnetism, gluons is gravity. Weak force is W and Z. And
Gravitons are gravity. Gluons are strong.
you are right. Thank you. Yes, that's correct. I also really enjoyed reading chapter 30, but you certainly don't have to. And I like that the book is pretty up to date because it was discussing CERN and the Higgs boson and specifically why it had to be discussed and where it comes from.
Why do the WZ ones have mass? Why are they so big?
Geometry. It has no size, no dimension. It's just an imaginary object.
Comes from you'll notice when they talk about the weak thing that they say that essentially it comes from beta decay, and beta decay's conversation comes out of beta decay comes out of the conservation of kinetic energy and momentum. You will notice they very, very, very carefully ignore any math, despite the fact that we've done kinetic energy and conservation of momentum with stuff on purpose. And that math is the answer to why these things have to be so big. All right, I'm just going to get you, I'm not going to finish the 11-minute, 50-second video, but you can watch it if you are somewhat more interested.
We start with a point.